you really influence China, particularly in analysis.
Okay, we start. So welcome to this session and section of numerical analysis and scientific computing. The speaker today is Zhang Bao from School of Mathematical Science of Zhejiang University, and he will speak about mathematical and computing issues in inverse scattering problem. So, John, we start.
Hello, everyone. I want to first thank the International Mathematics Union and the organizing committees of ICM 2022 for giving me this opportunity to speak. It's truly an honor. The title of my talk today is Mathematics and the Computation of Inverse Scattering Problems. I also like to take the opportunity to acknowledge some of my collaborators. This is a rather incomplete list of people who have made great contribution over the topics I discussed today. And the research I discussed here also funded in part by NSFC. So here's the outline of my talk. I'll first introduce the problems. I'll discuss some recent results on inverse medium problems, inverse source problems. At the end, I'll present some results on related topics and discuss the future research interests. Okay, so this work is really concerned with scattering and inverse scattering problems. So scattering is you assume you have a medium and a wave, a particle, a set of particles incident on the medium. And because the medium is inhomogeneous, so energy is distributed away from the medium. So the scattering problem is to study how the energy is being distributed along various directions. Mathematically, this often amounts to solve the corresponding partial differential equations. So what about the inverse problem? The inverse scattering problem in this setting is to use some measured information of the scatter field along with the information on the incident field to determine the medium or various characteristics of the medium. Okay, and that's the focus of my talk today. There are lots of applications of inverse scattering problems, particularly in exploration science. So here I list some of the sample application areas. For example, geophysical inspection, cloaking and stealth technology, optical microscopy, medical imaging, and optical imaging. So let me also mention some specific applications. One interesting application is the Radon transform. And this is a paper published over 100 years ago by Radon. As you can tell, this is the original publication. In this work, he solved the problem that is to reconstruct the function from all of the line integrals of the function over a domain. Okay, and so he came up with the so-called Radon transform and inverse Radon transform to reconstruct the function f. And this is perhaps one of the earliest work on inverse, mathematical inverse problems, and which led to some very interesting developments, both in application and mathematics itself. In particular, the very well-known computed tomography, CT technology. It's based on the concept of a Radon transform. And a nice consequence is that the two scientists won the 1979 Nobel Prize in medicine for their contributions to computed tomography. And this is a very active area of mathematics. So here, this example, you can see from travel time. So now this is in geophysics, the travel time. From this information, can you reconstruct over all the domain? Can you reconstruct the function Cx? And Cx characterizes the medium. Here is no longer a straight line. So it's a much more challenging problem. The second application I'd like to discuss is the seismic inversion problem. So here you have the setting is you send in acoustic waves into the Earth into the medium of the Earth. The idea is trying to inspect the medium to identify whether you have all your other natural resources. The information you collect is along the surface. So you measure this through receivers, the reflected waves. Mathematically, this model is the simplest one is the acoustic wave equation. So you can see that it's a very simple form. Here is the data is the additional boundary condition on the surface of the Earth. And you try to reconstruct the function Cx. This function is known as a velocity in geophysics. And the process is also known as a velocity analysis. So mathematically, you from additional boundary condition, you're trying to reconstruct the coefficient of the wave equation. And this problem is, although the form looks very familiar to many people here, but the mathematical problem, the inverse problem, is very challenging. In fact, some related problems are still completely open. For example, the boundary, there are a lot of results on boundary rigidity problem. And, but for length rigidity problem in differential geometry, largely open, a lot of open problems. So another problem I'd like to mention is the celebrated Calderón problem. This is due to the original problem was posed by A.P. Calderón in 1980. And it's a very short paper. And it's a very interesting problem. So what you have is what do we call the electric EIT problem. So you have a PD model, which is an elliptic model, and the coefficient is the conductivity. So from the voltage to the current map on the boundary, you're trying to identify this coefficient. So Calderón asked the following question. From this Dirichlet to Neumann map on the boundary, can you uniquely determine the conductivity, the coefficient of the elliptic equation? And in this paper, he solved the simplest case where he obtained the first uniqueness result when gamma is a small perturbation of a known constant. But Calderón's work generates a great deal of interest. As you can see that a lot of significant results have since been produced by some very strong analysts in the community. And especially in terms of uniqueness. For example, in the general case, two-dimensional case, Ostella and Pavrinta in 2006 published a work where they obtained global uniqueness when the coefficients, the conductivity is only L infinite, just bounded. Okay. but that's only in the two-dimensional case. The general high-dimensional case is still open. There are still a lot of problems with the Calderón problem, especially when you're trying to solve the problem numerically, because the Calderón problem, as now is well known, is very ill-posed. Due to the two mathematicians in 87, Alessandrini and Mondacci, they proved the stability estimate, and later on verified the optimal stability estimate to show that, in fact, for this inverse problem, the stability is a logarithm type. So meaning we know that means it's exponentially unstable. And even worse, we also know that later on, it has been proved that for Helmholtz equation and Maxwell equations, where at fixed frequency, you have the same sort of ill-posedness. So how do you resolve this ill-posedness? This becomes a very important question for solving the problem. Because we know that if you in practice, the data is always, there's always error in the measurement. And in order to guarantee the small perturbation, small error of the data of the measurement lead to small perturbation of the reconstruction, we need the stability. And that's why people try various remedies to recover the stability. People try the hybrid model and also maybe impose some a priori information on the coefficients, etc. In this work, we will use some frequency information, so additional data on frequency. And it should be pointed out that for Calderón problem, there's no frequency. It's a zero frequency. But even for the Maxwell equation, for the wave equation, a fixed frequency case, we know it's still ill-posed. That's a motivation to consider more than one frequencies. Okay. So as I mentioned, there are a lot of progress recently for inverse mathematics and computation for solving inverse scattering problems. However, there are still significant challenges remain. So here, let me mention a few. The first one is the nonlinearity. Even though the forward model, as I mentioned in the previous examples, for example, in the acoustic wave equation, the model PDE is a linear problem, but the inverse problem is nonlinear. So I recall that we try to reconstruct the coefficients from additional boundary conditions. That is a highly nonlinear. And another problem is the ill-posedness. The ill-posedness for the inverse scattering problem is the most significant challenge we have to face. So namely, we want to make sure that the small perturbation of the data will lead to small perturbation of the reconstruction. The third challenge is the diffraction limit. And this is significant because one tries to get improved resolution. Okay? So we like to know how far we can go. And this is also related to the uncertainty principle. So computationally, the inverse scattering problem are challenging because we have to solve the large-scale PD problems many times. It also involves high wave number problems. That's one of the challenging PD problems computationally. Another challenge is about uncertainty. So here, not only we have to worry about the data uncertainty, so errors in data, also model uncertainties. Okay, so and broadly speaking, inverse problem can be decomposed into 3 classes. So one is the inverse medium problems, and this is inverse medium problems. Another inverse source problems. The third one is the inverse obstacle problem. So you try to identify the interface, okay, from boundary measurements. And often we need to have some models. So models, by models here, really talking about the inspection methods. So here we use waves, electromagnetic waves, optical waves, acoustical waves, elastic waves, okay? And by measurements here, we mainly talking about the boundary measurements, and as well as multiple frequency data. For computation, numerical methods, I think we have to restrict ourselves to this optimization-based iterative methods. I should mention that there are a lot of recent works on direct imaging methods, but which is out of the scope of this talk. Okay, so as I said, we realized that for the Calderón problem, there's a fixed frequency, actually no frequency, 0 frequency. The problem is highly ill-posed. Then we want to look at, try to use multiple frequency data. We like to look at another extreme case. That is when you have all the frequency information. That would be the time domain wave equation. So let's see what happened. In fact, for the time domain wave equations, you can pose the same type of Calderón problem. So for the wave equation, you have a Dirichlet to Neumann map on the boundary. Can you uniquely determine the velocity or the coefficients of the wave equation? And this is the global uniqueness of this problem was first proved by using boundary control theory in 1992. We are more interested in the stability questions. For this, there are a lot of results and there are continued ongoing interest on the stability. Not only for this problem, but also on related differential geometry problems. But the previous results are mainly based on geometrical optics, and with assumption on there's no caustics. But we know that if you're in the field, you know that even for constant medium, this assumption may not be guaranteed. So for the wave equation, in the high frequency asymptotics, the geometric optics solutions blows up at caustics. Okay, so this is why that assumption has to be assumed. So our approach to resolve this problem is to use the Gaussian beams. So Gaussian beams is another high-frequency asymptotic method for approximating the solution of the wave equation. But for the Gaussian beams, since it's global and it builds up along each ray, so it will not blow up at the caustics. Okay. And by using combination of the Gaussian beams and the macro-local analysis, we proved the following stability results for the wave for the inverse problem of the wave equation in the presence of the caustics. And this is some of the technical ingredients of the proof. And so the result is the first stability result for the inverse problem of the wave equation with caustics. And we further extended the result to study the lens rigidity problem in differential geometry. and obtained the first stability result for the non-simple metric case. Okay, now we go back to the numerical solution of the inverse scattering problems. So we look at the case. I probably should mention that for the time domain problems, the stability estimate is very nice. So if you can resolve the problem, you get the Lipschitz type stability estimate. So we have a Calderón problem, fixed frequency, very bad, and the time domain where you have all frequencies, Lipschitz type. So now we look at how to solve the problem. The idea, the objective is to develop data-driven stable reconstruction algorithms. The method will be able to handle, to systematically choose the initial guesses and to be able to overcome the challenges, the nonlinearity and the ill-posedness of the inverse scattering problems. So let me, to discuss our method, let me use an example. This is a 3D Maxwell electromagnetic inverse scattering problem. So the medium, this is a medium function, is a QX. So we shine a plane wave, so incident on the medium, and the energy is being distributed along various directions because of Q is inhomogeneous. Then you go back to the time harmonic Maxwell equations. This is, if you get rid of the magnetic field, this is what you have. Here, K is a wave number representing the frequency, and Q is characterized as the medium of the scatterer. ET is the total field that consists of two parts, the incident field plus the scatter field, whereas the incident field solves the whole corresponding homogeneous problem, okay, with the constant coefficients. But the scatter field is satisfied if you plug this in and you do a simple algebra, this is what you get. The scatter field satisfies this inhomogeneous equation, and along with a standard radiation condition as infinity. We have to pose this to get the uniqueness for the scattering problems. Okay? So now the question is, from the boundary measurements on the boundary of the electric field, can you then determine the medium Q? There are lots of results because of the significant applications. A lot of results have been obtained, both in the case of fixed frequency and multiple frequencies. So here's a long list of the works. I also would like to refer you to a topic review published in 2015 on these topics, along with references. So to understand the method, let's look at this, again, look at our model problem. So here, for simplicity, we use, instead of look at the radiation condition, this is the exact radiation condition, I'm looking at the first order absorbing boundary condition on the boundary. Okay, so this is the approximation of the original problem, but it's a good approximation. Then I also introduce a test function. So the test function satisfies of the following form is satisfy the homogeneous Maxwell equation. The incident field is a plane wave. So now I multiply both sides of the equation by my test function integration over the domain. So integrate over the domain. And simple integration by parts, this is identity what I get. So I move the Q, intentionally move the medium, the part involved medium to the left. As you can tell, this really looks like a Fourier transform of the medium function. On the right-hand side, you have two terms. The first term is rather nice because it's really the boundary data. So the tangential component of the electric field on the boundary. The rest is all given. So this is your boundary data, very nice, okay? But what about the second term? That's the problem. Not only we have a Q, we also have a function that is nonlinearly depend on Q. So the scattered field and the product. This is why the inverse problem is nonlinear and is ill-posed. But if for any reason you can get rid of this term, okay, then you have a good problem, right? Then you have this is known as a linearization. So what about the criterion? If for any reason you know this term is small, then you can get rid of it. And there are criterion you can guarantee that this term will be small. For example, if the domain is small, if the medium is small, or if the scattered field is small, so corresponding to a weak scattering, okay? So in any case, if this is a small, you get a linearization. So problem is solved. You get a very nice form integral equation to solve for Q. But you don't get the whole Q. Notice if you do this, what you only get is the Q up to the mode of 2K. So K is the wave number. But that's good enough for initial gas. So this is what I'm talking about, the systematic way to determine initial gas. Okay, so here's the method. We call the algorithm beyond Born, because a lot of people in practice would simply use the linearization or the Born approximation as a solution for the inverse scattering problem. Later on, you can see that from the examples, that could lead to big errors, sometimes over 90% of errors. So here's the method. We started with the initial gas obtained from Born approximation. So this is the Born approximation, give you an initial gas. Then, since we have multiple frequency data, so each time we march along the frequency. Every time we do a one-step linearization. So we linearize with respect to the frequency. And so each step, we solve two forward problems. So one forward problem along with adjoint problem to determine this correction term, delta Q. So every time we update, we keep on going until we run out of the wave numbers. Okay, so this is and turns out that this is very stable. So you get we get the results allowed by the data. So let me show you an example. So this is a 3D medium, and it's hard to see a 3D medium. So we look at the different slices. Here's the exact solution, the scatterer. Okay, so then you do we do Born approximation at the low frequency. Okay, the lowest frequency we use is this 0.5 pi, and you get this is what you get, not even close. Okay, not even close. So that means the Born approximation is not a good approximation when the medium itself is not very smooth. In fact, it gives you this what do we call the average of the medium. But you continue march along the process. You do the linearization along the wave numbers, and you get improving result. In a few steps, this is what you get. Very good reconstruction. Okay, so not only you get a good reconstruction, they're stable. We believe there are some convergence results behind. But in order to prove any convergence, we need a stability. And this is until now it's still an open problem. So what we are able to prove is the one-dimensional case. So here's the one-dimensional case. We're trying to get the stability estimate when you have a multiple frequency data. So in the 1D case, this is the Helmholtz equation over a unit interval, so 0, 1. So again, this is the wave number and the medium. So the scattering waves corresponding to the left and right excitations takes the following form. So this is the incident field. And your data is your boundary measurement, displacement. So this is your boundary measurement. And the inverse medium problem is to reconstruct the medium function Qx from this boundary data over an interval of frequency. Okay? So this is the inverse problem. And let's see what we get. So this is the stability we get. And you can see that the stability assumes that the Q and Q theta are two medium functions corresponding to two sets of measurements. Okay? Then you can see that this is the difference is bounded. So you have this Holder type estimate. So eta is an explicit, we have an explicit form of the function of K0. K0 is the highest wave number. Okay? It's an increasing function. And when K0 goes to 0, so corresponding to a fixed frequency, then it goes to 0. So this is a very ill-posed situation. And when K0 goes to infinity, it increases along, but get to it's still less than 1. Okay, so this is a Holder type. And the ideal proof based on trace formula and some properties of the Schrodinger operator, along with unique continuation results. So if you further consider uncertainty, so we know that when you have so for the stability estimate, it's usually important to consider the uncertainty principle. With that in mind, and you look at the observable part of the medium, is defined by using the truncation of the trace formula. Then you actually get a very nice estimate. So this is what you get, the observable part of the medium. So the difference of two experiments can be, you get this Lipschitz type estimate. Okay, and this is very promising. In practice, this is what you should expect. And but let me remind you that the multi-dimensional case is still open. So the second class problems I like to consider is the inverse source problems. So here you look at this simple model. It's a 2D Helmholtz equation with constant medium. So here S is a source function. So we have a radiation condition at the infinity, and from the question, the boundary measurement away from the source function. So it's a source with compact support. And again, we look at multiple frequency. So you have a range of frequency. You're trying from this boundary measurement, trying to determine S. Okay. This is also a classical problem with a lot of results, but mainly we can see that even though the problem, you can see the problem is linear. So to determine the source function is in this setting is a linear problem, but it has all the problems of inverse medium, difficulties of the inverse medium problems. For example, non-uniqueness. If you only have a fixed frequency measurement, it is well known that this inverse source problem, does not have uniqueness. because of possible trapped rays of the source function. So it never gets to the boundary. And the opposedness at the fixed frequency case is also similar to the inverse medium problems. So here I want to present the stability result in the case of elastic wave scattering. So for elastic waves, we know this is much more difficult. So you have a different type of waves, shear waves and pressure waves, and they for the medium, and you're trying to get to solve the scattering problems. But this is in fact, for geophysics, most of the models should be the elastic wave scattering models. So for model equation, we consider elasticity problem. The operator is the Lamé operator. So you can see this is the operator itself. And the source function, f is the source function. So on the boundary, it's called the traction operator, elasticity. And so the inverse source problem is to determine f from the boundary of the pressure function on the boundary over a range of frequency. So k is the highest wave number. And for the elastic scattering and inverse scattering problems, there are a lot of recent works, both in terms of the forward scattering problems and the inverse problems. For example, we have recently, by using this recursive linearizations, we're able to solve the inverse elastic medium scattering problems. And so the stability result in this setting is the following result. It's very interesting. Along the same line as I discussed, so I want to give you, to show you this result. You can tell that here's the estimate. So remember f is the source function. So with the two terms on the right-hand side. The first term is really nice. What it says is a Lipschitz type estimate. Okay, so you have a Lipschitz type estimate plus something I would call a tail. But this term, if you look at it, analyze it carefully, you have the highest wave number. As k goes to infinity, this term goes away. Okay, so this is when the highest wave number getting really large, then you have a well-posed problem. Okay, so this is very interesting. And so let me also mention some related work along this direction. So one result is about inverse source scattering problems. So trying to simultaneously reconstruct the medium and then point source for the Schrodinger equation. We also recently obtained some result, the stability for reconstruction of multiple point sources for the inhomogeneous Helmholtz equation. Another related work is the inverse scattering with randomness, and this is to reconstruct random periodic structure from boundary measurements of the scatter field. So we developed a novel combination of Monte Carlo technique, and since we're using multiple frequency, so we use a similar this recursive linearization or continuation method, and the uncertainty quantification for the random structure using the KL expansion. Finally, this is a deep learning-based algorithm for solving inverse problems. So we proposed a weak adversarial networks, so one for solving PDEs and the inverse problem. The idea is that if you have a PDE problem with a weak formulation, we're able to to come up with this method, this technique solving the high-dimensional problem. So this is the deep learning method. And we also applied the method to solve corresponding inverse problems. One example we studied is the Calderón problem. So and turns out we get very good results. This is still amazing how we are able to get very nice computational results for the Calderón problem. Let me also discuss some future directions for inverse scattering problems. The first direction, I already mentioned in my talk, probably a couple times, about the stability analysis for multiple frequency inverse medium problems in several dimensions. And this is extremely important for understanding of how the frequency information can be used to solve the inverse challenging inverse scattering problems. The second direction is about the multi-scale problems, where not only one tries to identify medium or interface obstacles, one tries to get very small features of them, so namely nano characterizations. And because of extremely small scales, quantum effects will take place. So one needs to deal with the model equations that beyond the classical wave equation, Maxwell and Helmholtz equations. As a third direction, we like to study about the inverse problem with incomplete data. So standard theory fails. This is a limited aperture, poor initial gases, faceless data. So in this case, although we don't have enough data to guarantee the classical sense of uniqueness, we still need to solve the problem. So that presents a nice challenge. So the next direction, future direction for future study, is about the inverse problems involving uncertainties, especially for inverse medium problem and inverse obstacle problems, where the solution depends on medium non-linearly. In the case of obstacle problems, the solution depends on the obstacle non-linearly. So if you have uncertainties in the medium or the surface, the problem becomes extremely hard. We don't have the machinery to study this type of problem systematically yet. So finally, I'd like to draw your attention to the ever-growing study of new methods like deep learning, optimal transport methods for numerical solution of the inverse scattering problems. I believe this offered a very nice alternative for future understanding of numerical methods for solving the inverse scattering problems. So to conclude, inverse scattering problems are exciting and fastly growing area of mathematics driven by interdisciplinary applications. Many basic mathematical questions to be addressed. This is exciting and very problems likely have impact. And in fact, the computational methods are in high demand. With that, I'd like to conclude my talk, and thank you for your attention.
Thank you very much, Zhang, for very interesting and thought-provoking talk. So I just would like to remind to the audience that they can ask your question directly via Discord chat. So thank you very much. And
Okay,
goodbye.
thank you.
Bye.
Yeah, it's a pleasure to meet you here.
Thank you.
Okay, thanks a lot. Okay,
Goodbye.
so we're done. Very good. Thank you.
Bye.
Okay. Go back to the green room.
Okay, goodbye, Mr.